Thank you very much for the invitation. So I'm very happy to be here. As I said, great setting, great people. And I will talk about mostly completion for the spectral metric of the space of Lagrangian and Hamiltonian. So this was actually started in Vincent's PhD dissertation. And so recently we've added a number of things. So the first thing will be spectral completions. And so let's start from a Liouville manifold. And if you have now two exact Lagrangian submanifolds, so this will be exact Lagrangians. So I should say that everything works much better, but I will not do it if by exact Lagrangian you mean a pair of L and the primitive FL of the restriction of lambda. So exact Lagrangian means that lambda restricted to L is the FL, and of course lambda to L prime is the F of L prime. And well, it would make the talk a little bit cumbersome to always carry the FL or FL of FL prime, but it actually makes life a little bit easier when you concretely do that. Okay. And now is sort of equivalent to L prime if they are isomorphic objects in the Fukaya-Donaldson category. And this means, I mean, I don't want to go into details, but this means that fh star of L and L prime is isomorphic to h star of L, which is also isomorphic to h star of L prime. But it's a little bit more than that. You need that this isomorphism be natural somehow. Okay. So in that case, you can then define spectral numbers. So if you take alpha, for example, in h star of L, which is the same as h star of L prime, or fh star of LL prime, you associate C of alpha and L prime. And for example, if you do that, you need to know what the primitive of df of lambda restricted to L and lambda restricted to L prime is. If you change them by a constant, it will switch this quantity by a constant. Elsa, you have an idea of what's going wrong here. So for LL prime, now for L equivalent to L prime, one can define a spectral distance gamma of L and L prime. Okay. Now let's choose an equivalence class. And let's denote it by L of M d lambda. Okay. So I have a distance on this space. Okay. And what I can do is take so this is a metric space with the distance gamma. Okay. So gamma is the distance, and you consider L hat with the same distance gamma. So this is the completion of L gamma. Okay. So question 1. Is this useless? Well, that's a real question. Actually, it took me a while to come up with this question, and I actually didn't come up with this question. It was asked to me in a talk by Michele Stecconi. And the reason why you can ask that is that you have spaces which are called Polish spaces, which are spaces such that you can keep the same topology, change the metric, and it becomes complete. Okay. So from this perspective, of course, if you know only the rational numbers, then it makes sense to take the completion so that you get all real numbers. But if by some chance you knew all irrational numbers, then from the topological point of view, not from the algebraic point of view, but from the topological point of view, there's really no point in adding the rational numbers. Okay, of course, from the algebraic point of view, it's a little bit strange because you would know 2 square root of 2, you would know square root of 2, but you wouldn't be able to multiply them or divide them, so that would be a little bit strange. Okay? But in principle, what this says is that you're getting most numbers if you know all the rational numbers, and the more important thing is that Bayes' theorem holds if you look at only irrational numbers, because you're in the completion of a countable set, so the irrational numbers will give you an open, I mean, will satisfy, the irrational numbers will satisfy Bayes' theorem. Okay? So the answer here is, it's not useless, is that this space here, that's not very difficult, but it actually requires a proof. Well, it's not a Bayes space. So you're actually adding lots of stuff, and which is essential. Okay? Now, what I should say is that you can do the same, of course. Similarly defined. So if you take what I call d ham of m d lambda, this is the set of Hamiltonian maps, which is the set of time one maps of some Hamiltonian. So phi ht is a Hamiltonian flow. Okay. And you have a similar norm. Gamma. Okay. Well, depends on whether you're looking at compact objects or non-compact objects, but it could be just gamma for the graph of M, for example, or you can define it directly. And so you can get the completion d ham hat of n d lambda. Okay. And maybe diffeomorphism. Okay. Yes, that's the French diffeomorphism Hamiltonian and not Hamiltonian diffeomorphism, so it should be, otherwise it will be ham D, but. So the remark is that d ham acts on the set of Lagrangian. So what I should have said, which is clear, is that if two Lagrangian are Hamiltonian isotopic, they're of course in the same Fukaya-Donaldson class. Okay. So this d ham preserves L, and it acts on L by isometries. And so you get an action of d ham hat in the end on L hat. Okay. It's only one at a time. Yes, sure.
So are you working for the closed sectional program, or are you?
Oh, sorry, they're all closed. Yes, all manifolds are closed. I should have said that before. Except M, yes. That's a good point. Yeah, usually say all manifolds which can be closed are closed. And if R2n occurs, of course, it's not closed. So let me give maybe some examples that you already know somehow. Or maybe, no, maybe let's start with something slightly different. So there's something which is deeply unsatisfactory with this, is that an object, what is an object in L hat? Okay, so or the Ham hat. Well, by definition, it's a Cauchy sequence of Lagrangians or a Cauchy sequence of Hamiltonian, okay, and that's it. Okay. So a priori there's no subset associated. So the question is, can one associate a subset of M to an element in L hat? Okay. And the answer is yes. Okay. And it's called the gamma support. So there was already a definition of support in Vincent's thesis, but this is a little bit different. Okay. So let me write down what the support is. Well, so let L belong to L hat of M d lambda, then Z in M belongs to the gamma support of L, which I denote by gamma sup of L. Okay. If for any neighborhood U of Z and any Hamiltonian diffeomorphism compact supported in U, yes, should I say does not belong? Does not belong. Where's the eraser? Ah, here. Is not in the gamma support. And then there exists U. Yes, sorry. Such that any phi supported in U is such that, and I will write it maybe in a strange way, but gamma phi L is 0, and this is the same as saying that phi of L is equal to L in L hat. Yes?
So when you denote the ham of U, does it mean that the time one map is supported in U or the whole isotopy?
The whole isotopy. So this is, yeah, by compact supported in U, and I mean the whole isotopy. Maybe it would be true for. Okay. So somehow, I mean, this makes sense. You have, so sort of trivial example, if L is just a regular Lagrangian, so you have your submanifold here, what it means is that if you're at this point here, if you take Z here, well, if you look at diffeomorphism in a small neighborhood, when you apply phi to L, it's not moving L, so L doesn't change. And on the contrary, well, that you have to prove something, but it's not that difficult. If Z is on L, then you can find the Hamiltonian isotopy, which actually moves so this will be phi of L, which actually moves L away from itself. Okay. So let me give some more examples of objects which naturally live in the completion. Well, the first thing, for example, is that if H is a continuous function, let's say compact supported to make things easier, on the manifold M, then it has a flow in d ham hat of m d lambda. And this is because, so the reason is that gamma of phi is less than the C0 norm of H. Okay. So at least if H is compact supported, you have finite quantities. Okay. So if you have a Cauchy sequence for this norm, okay, you will have a Cauchy sequence for this norm here. And we'll see maybe at the end of the talk, if there is time, that if you have a continuous Hamiltonian, let's say compact supported, then it has a flow in the completion of d ham. And sorry? You have a family FHT which lives in d ham hat, okay? And so this operation coincides with the usual operation of taking the flow of the Hamiltonian when H is C infinity. Okay.
Why is this an example? This is an example
of elements. This is an example of elements which live naturally in d ham hat and which do not live. I mean, you don't have an ordinary flow for a continuous Hamiltonian. Okay. And we'll see maybe at the end of the talk that in fact you even need less than that. You can allow some discontinuities. Yeah.
Can you describe the flow of
You could, but I'm not going to do it. So a similar case, if you have so a similar case. So due to result of Buchowski, Humilière, and Cefadini, if phi is the C0 limit of phi k, where phi k belongs to d ham, okay, of m d lambda. So which means that phi is a symplectic Hamiltonian homeomorphism in that case. Then phi actually lives in the ham hat. Okay. That because the gamma norm is controlled by the C0 norm of the maps, not of the Hamiltonian of the maps. Okay. That's a very deep result, okay, which is used here, but it tells you that these objects actually belong there. And some of these objects, well, some of these objects appear more or less naturally, but for example, having continuous Hamiltonian is something that occurs naturally. For example, if you do symplectic homogenization, okay, then there's no way of getting regular Hamiltonian. You will always get continuous Hamiltonian a priori. Okay. So question, I think that's question 3. In view of that is how big or small can the gamma support of L be? For the moment, you don't know anything. You could say, okay, sometimes it's empty, so it doesn't really help. Okay, and so let me give an answer, and the answer goes, well, there are several aspects to the answer, but one goes through a definition, and the definition is what I will call gamma coisotropic set. And this was also a slightly different definition, is due to Usher under the name of locally rigid. And this says the following, so let V, so now be a subset. Well, you can actually work in any symplectic manifold. We can stick with the ones we're interested in here. Okay. And let a point Z in V. We shall say that V is gamma coisotropic at Z. Maybe I will write, if I will write it here. So let me say what's the idea before I write down the definition, and then you will see whether what I write is compatible with what I just said. So the idea of gamma coisotropic is that it should, if you want to locally move your manifold V near Z, okay, let's say you want to move it outside a small ball, then it should cost you a certain amount, and cost means the size of the gamma of phi. Okay, so if you take a Hamiltonian isotopy which displaces V outside of a small ball surrounding Z, okay, this should have a strictly positive cost. You cannot do that for arbitrarily small cost. So you first have to, so I'm putting an epsilon here to make things local. Okay. So the eta will be the ball that I want to displace. And so there exists some delta strictly positive such that if I have some Hamiltonian map compactly supported in the ball of radius epsilon, and such that phi of V does not intersect the ball of radius eta, then gamma of phi, should be strictly greater than delta. And I hope this coincides with what I just said. Okay. So you're localizing, so you have your V here. I have the point Z. So first I will take a ball epsilon, because this is going to be a local property here. So this is a ball of radius epsilon. Then I choose a smaller ball of radius eta, which will be here. And then I want to move V outside of this ball, so I want to deform V like this by something which is supported in the ball of radius eta. Okay. And now what I require is that this map which sends V to this red image must have gamma bounded from below. You cannot do it for arbitrarily small cost. Okay. Yes?
What do you need epsilon? I don't understand.
Because you need epsilon because otherwise it's a non-local property, so maybe you could move it by going sort of very far away and doing complicated things far away. And I think you have to look into Mike's paper. I think there are examples where this can happen. So you cannot do it locally, but you can do it globally. Okay. So you have to, I mean, if you want a local property.
Is there a specific reason why it's called coisotropic? Because I don't see it.
There's an excellent reason. So first example, sorry, and I should add that we say that V is just gamma coisotropic if it is coisotropic at all points. If it is gamma coisotropic at all Z in V. So examples. So example 1, if V is a closed manifold, so closed smooth manifold, then V is gamma coisotropic if and only if V is coisotropic in the usual sense. Okay. So I guess that's a good reason for calling it gamma coisotropic. Second example, which is a little bit more subtle, here it's crucial to say closed. Okay. Let's look at a very simple case. V is 0, 1, the interval 0, 1 in R square. Okay. Am I supposed, is it okay if I just erase the board, or do I have to do the wall cleaning stuff? It's okay? Okay. Well, maybe at some point during the talk I'll have to do it, but anyway. So I have the interval in the plane, and first thing is that V is gamma coisotropic at any point in the open interval. Well, that essentially follows from the first one, because if you're looking at a point here, you cannot see whether the manifold is open or closed. I mean, it's a local property, okay? And locally, this is a Lagrangian submanifold in R2. Okay, so by what I said before, it should be gamma coisotropic. But everything changes here, okay, is that V is not gamma coisotropic at Z either 0 or 1. Well, why is that? You can sort of guess that if you're at this point here, you can just push in this direction your segment, okay? And this you can do with extremely small cost, because you just take a Hamiltonian which has a large derivative in this direction on this segment, okay? So it can be C0 small but has a large derivative, so you can push with an arbitrarily small cost here, okay? So you have to be a little bit careful. I mean, the gamma coisotropic coincides with the usual thing in and so now I can state theorem 1, which says that let L be in L hat, then the gamma support of L is gamma coisotropic. And there's a consequence to that, which is not that difficult to prove. I mean, it's not completely trivial, because this gamma support can be rather complicated. But in particular, the Hausdorff dimension of the gamma support of L is greater or equal than n. So this is just to show you that it cannot be arbitrarily small. There's another theorem, actually, maybe I will call theorem 2, which goes somehow in the same direction, which says that if L1 and L2 belong to L hat of M d lambda, then the intersection of the gamma support is non-empty. And there's even something more, if you want. So theorem 3, so this is joint work with Marie-Claude Arnaud, Vincent Humilière, and myself, is that in T star n, so you can do that in the cotangent bundle for n closed. Okay. So T star n is not closed, but n can be closed. Then the projection on the base induces an injection in cohomology. Always, otherwise it's not defined. When I write L, it means I chose a class, an equivalence class. And so if in T star n, so if pi is the projection from T star n to n, then pi hat from the cohomology of n to the cohomology of the gamma support of L is injective. Okay. So this is another reason to believe that it cannot be too small. Now let's go in the other direction, how big this can be. And the answer is that it can be pretty big. And for example, you have what I call Peano Lagrangians. For example, let's say in L hat of, let's say, the cotangent bundle of Tn, but you could do that in any cotangent bundle, okay, such that the gamma support of L is the union of the zero section, which is not very surprising, and some cube of essentially arbitrarily high dimension between 1 and n. So for example, if for n equal 1, it means that you can have something so this is the zero section of S1. So you can have something with gamma support, the union of the zero section and the square. And let me sort of shortly tell you how you do that. So how does one do it? Well, you have to build a Cauchy sequence. Okay. And so the Cauchy sequence will be as follows. So you have here the zero section. Here you have your square. So I'm doing that in dimension 2. So I look, for example, at all rational points, and for each rational point, I arrange that some member in the sequence here will go to this point. Okay. So, for example, I choose a first point here, and then I can continue. So here, I will then add some small thing like this, and you have to control the areas involved. Okay, that's the only yes.
I find against the previously erased white chalk, everything you drew inside the square to be invisible.
So this means I have to do some cleaning, maybe? Or I could use red. Okay. So you start by constructing a mushroom like this, and then you continue to another mushroom like this. Of course, you have to do the same thing symmetrically, so it's Hamiltonian. Okay, so here, I don't draw what's on the other side, it's just the mirror image. Okay, and so you have to be careful with the areas which are involved here, and you have to make sure that you sort of go through any rational point. And in the end, what you get is something such that the gamma support contains the whole square. And you can also see something more. You have to be a little bit careful. Can you do the whole annulus? Maybe. You have to be a little bit careful. Yeah, maybe you can. I think well, I will give an example of something, and then you tell me if that answers your question. If it doesn't, I will try to answer the question. Okay. Well, there are theorems from starting from Fukaya, Seiden-Smith to Abu Zaid Krag, which tells you that there's only one class in the cotangent model of a compact manifold. Okay, so that's something I have to. Sorry, I can't do math and housekeeping at the same time. Okay. So natural question here is so this is question probably 4 or something like that, 5. Does the gamma support of L determine L? You could say maybe the only thing that there is to L is actually its gamma support, and the answer is no. And the example is again the Peano Lagrangian, for example. But that's not the only example. I will give you another example. Okay. Because if instead of starting at where I started here, my construction, I start somewhere else, okay, well, the distance between the two Lagrangian will be essentially the area of the first mushroom, maybe minus the area of the smallest one. But if I construct the next one to be extremely small and converging fast enough to 0, I still get a distance between the two of them. And so the two of them will have the same gamma support, which will be the square. Okay? but they will be at a positive distance. So it's easy to construct two Cauchy sequences, okay, which have a limit. Both have a limit, of course, by definition, and they both have gamma support to be the square plus the zero section, but they are bounded, the two Cauchy sequences are bound away from each other. Okay. Now I can give another example, so that's example 1, and now you can example 2, so I don't know if the example 2 will answer your question. I just need to make the example 2, well, it's not that complicated, I just, oops. So this is the gamma support of L, and it's also the gamma support of L prime. So I have to describe what L and L prime are. So L is going to be something like this. So this is the sequence Lk, and the sequence L prime k is just, well, I'm sorry, the drawing is not that good, okay? But you see that the distance between Lk and L prime k is essentially the sum of this area here and this area here. So it's positive, okay? It's easy to see that as I sort of shrink here, I get a Cauchy sequence in both cases, and it's easy to see that the gamma support is going to be this. So here you have an example of something which is the gamma support of two objects in the completion, and a conjecture that these are the only elements which have this gamma support. Okay. So that's sort of, as many conjecture, it's just a conjecture motivated by a lack of examples. So the conjecture, if the gamma support of L is, let's call V, this set here is V, then L is either, well, let's call this L1 and L prime 1, so that's L1 or L prime 1. And there's a question, so far I was quite well organized, I only asked question I could answer, but now there's a question I cannot answer, and it says describe the set of gamma support of L such that the set of L, so is V. So the set of L such that the gamma support of L is V is compact. And the answer, I have no idea. But of course, in a complete space, it's important to know what are compact objects, and if, so in this example, in this example, I would conjecture that the set is compact. And I would sort of maybe conjecture that the condition should be that V should have sufficiently small dimension. So if V has dimension n, in some sense, I don't know exactly which sense, but maybe Hausdorff dimension or something like that, then maybe it's true. Okay. Yes, sure. Yes, so that's the next question. Exactly. So the simplest case, which Egor pointed out, of course, is what happens if the gamma support is a smooth Lagrangian. So that's a theorem So the theorem is due to, sorry, no. Zano, Guillermo, Humilière, EK, and myself. And it says that if gamma support of L is smooth, exact Lagrangian, then L is the same as the gamma support of L. So what does it what does it mean? L is an element in the completion. I said that the gamma support is a smooth exact Lagrangian. Okay. So maybe that, sorry, I should have said that this is in T star n. Okay. So if so the gamma support of L belongs to L, so belongs to L hat. Okay. And here I say that the element L here is actually the element in which is a priori in L hat, actually belongs to L, and is of course equal to the gamma support. Okay. And this, I won't give you the proof, but the proof uses, on one hand, uses sheaf theory, and uses a version which, well, probably I won't have time to describe. So a weak version of the nearby Lagrangian conjecture, which is due to Marie-Claude Arnaud, Vincent, and myself. There's a problem in the statement? Maybe. So what's the problem?
If you want to say if it's a smooth exact Lagrangian V, then L equals V.
Well, but then V is equal to gamma sup of L, which is okay by transitivity of the equality. No? No, it's that's better? Okay.
Okay, I think I see what you're saying. I would erase equals equal to that.
You can. So, well, whatever. Sure. So here, if you say that it's a smooth manifold and it has dimension n, it's automatically Lagrangian. Okay, so in some sense, this is the minimal possible size of, if it's smooth, it's the smallest possible size of the gamma support. What we need in the proof is to add this exact, which shouldn't be required. Okay, it should be an automatic consequence of the fact that it's the gamma support. But well, I don't know what I can say, Stéphane. Maybe we could prove it, but it's not that easy somehow. Okay, but at least the conjecture is that you could remove the exact here. Okay, so let me give some applications of all this. Okay. So the first one, so this is joint work with Stéphane. So in T star n, so this will be in T star n for n closed. you have a quantization map, so to exact Lagrangian. So as I said before, you don't have to choose a class because there's only one class in a cotangent bundle, okay, due to so to an exact Lagrangian, you can associate a sheaf, and the connection between the two is that the singular support of the sheaf so such that the singular support, so here I have L, and here I call this FL. The singular support of FL is actually, well, by abuse of language, I will write that it's, or maybe I will write as the reduced one, let's call it. Then I don't need this bracket. Yeah. Okay. So the singular support is the direction in which the sheaf changes in the derived category. So these are directions where the sheaf changes, and this is known to be involutive submanifold, which is sort of definition of isotropic, okay, using cones and things like that. Okay. So the reduced, so RS of F is the singular support of F. So this belongs to T star of n times R. And here you have the last coordinates, which are tau and t. And so I intersect with tau equal 1, and I do symplectic reduction. So by symplectic reduction, you go from something in T star n times R to something in T star n. Okay? And that's what's the reduced support of FL. Okay? And then, so this quantization construct, and there's two ways of constructing it, one using Floer homology and one without using Floer homology. So Stefan did it without using Floer homology, and I did it using Floer homology. And so there's a first, so here we have RS, okay, sorry. Now this map Q is an isometry. So for gamma on one side, so here you have the metric gamma, and here you have a kind of interleaving metric. Okay. And for this interleaving metric, this map is an isometry. So for gamma, let's say D interleaving, so extends to a map from the completion here to the completion here. But the good thing is that the completion here, so the C means constructible, so the completion will give you what are called locally constructible, but these are still real sheaves. So an advantage of this construction is that here I'm getting extremely abstract objects, which are when I complete, which are Cauchy sequences and so on, but here I still get real sheaves. Okay. And the theorem so the theorem we have is that that's also a theorem with Asano says that the reduced singular support of Q star of L is just the gamma support of L. So all this was somehow useless. I mean, except that you have to prove, well, not completely useless for a reason you will see. Okay. But in a way, this gamma support, once you do this quantization procedure, is nothing else than the singular support that sort of, and coming down to this. So there's another theorem which is related to this from Stefan and myself, which tells that if f, so that's a different thing, but if f is any sheaf in N, then the singular support of f is gamma coisotropic. So that's another illustration of where gamma coisotropic comes into play. And the advantage of this with respect to the Kashiwara-Shapira involutive definition, so in Kashiwara-Shapira they say the singular support of a sheaf is involutive, which is something which is defined using the tangent cone to the set. But the tangent cone to a set is only invariant by C1 maps, or C1 diffeomorphism. While here you have some property which is invariant by C0 symplectic homeomorphism. So it's much, in a way, it's much more natural, and it's easy to prove that gamma coisotropic implies involutive in the Kashiwara-Shapira sense, and we even have some examples of sets which are involutive but not gamma coisotropic. Okay. And maybe in the last two... yes, sorry. So in the last 2 minutes, I will try to give another application. I mean, I really... which has nothing to do with sheaves. I see some people are relieved. So this is extension to higher dimension of Birkhoff attractors, and so this is again work in common with Marie-Claude, Vincent, and myself. Okay. And the idea is the following. So take a map psi, let's say from T star n to itself, but you could do that in a symplectic, in a Liouville manifold, okay, such that psi star omega is A times omega. So these are usually called dissipative maps, okay? And A is a constant, which is a constraint in dimension 2, but is not a constraint in high dimension. If it's a multiple, if you say that this is a function, the function has to be constant in dimension greater than 2. Okay? Then there's something which was done by Birkhoff in 1934, and also completed by Marie Charpentier, about the same. Oops, sorry. I think maybe 36, which is doing the following. So you take the case of the annulus and look at the images. So I have an annulus, and I look at the image. So the images will be like this, okay? And then you iterate. Okay? And in the end, what you're going to get, I will try to use the red chalk, is something like this. Well, it will have corners, for example, it will have spikes. Okay. Okay. So the image of this annulus, as you iterate, is going to just go around here. Okay, on one side and the same on the other side, okay, until it converges somehow to this red region. So what does Birkhoff do? Well, he takes his scissors and cuts out all these kind of spikes. I mean, he does kind of pruning. Okay, so there's and this gives you what's called the Birkhoff attractor. And it has a certain number of properties that you can show, and in particular, it was shown by Marie Charpentier that this can be an indecomposable continuum. Okay. Indecomposable continuum means a compact connected set which is not a union of two compact connected sets unless the trivial decomposition, okay, of everything and the empty set. So this can be quite complicated object, so it doesn't look really like what I did. Okay. So just to conclude, what can we do in higher dimension? Well, in high dimension, we can make psi act on L hat, and it's going to be a contraction. But now we're in a complete space. So there's a theorem that tells you that you have a fixed point. Okay. But the fixed point is useless because it's an abstract object in an abstract space. Okay. But you can take the support, which is a concrete object in a concrete space, okay, and ask, well, what can you say about this object in high dimension? Well, we proved a number of theorems which give you property of this object, which we call generalized Birkhoff attractor. And then you can say, well, can I understand what Birkhoff did in terms of this completion? Well, there's one thing you can easily understand, okay, is that if my object, my Birkhoff attractor, should be the gamma support of something, it has to be gamma coisotropic. But this red set cannot be gamma isotropic because it contains the endpoints of an interval, and we showed at the beginning that the endpoint of an interval, at the endpoint of an interval, you're never gamma coisotropic. So maybe Birkhoff knew about gamma coisotropic, but you can say a posteriori that the reason why he removed this is that because you want to get a gamma coisotropic set. And you can actually prove that the Birkhoff attractor is exactly the gamma support of the fixed point that you get by psi. And I think my time is more than over, so I'm sorry for going over time, and thank you for your attention.
Okay, any questions?
Yes?
So for the gamma support of some Cauchy sequence L, does it still have a lot of intersection of some other Lagrangian?
Yeah, so I said, well, two of them will, if the cotangent bundle, two of them will intersect, in particular, because the gamma support of the zero section is obviously the zero section, they will intersect the zero section. You can also prove that they will intersect any vertical. Okay, so it has, but I mean, yeah, it has somehow the same properties as what you expect. Yeah.
So let's take some kind of closure or some subset in the minimal possible gamma quadratropic subset contained. So what if you take the closure of the closed unit interval on the cotangent bundle?
So you want to consider what? The smallest gamma coisotropic set containing the unit interval. I think it's going to be it doesn't make much sense, I think, because if you intersect two of them, it's not going to be gamma coisotropic. But I think if you take, for example, a circle, any circle, it doesn't have to, see, gamma coisotropic doesn't contain many topological properties. So gamma supports have more topological constraint than just regular gamma coisotropic. Okay? But if you have a segment here, well, any closed curve like this will be gamma coisotropic, and if you remove any point here, it's not gamma coisotropic anymore. So in this sense, it's minimal. Okay, but I'm not sure Yeah.
So it's clear it's always if it contains Lagrangian closed leaf or something like that.
No. Well, for example, in this case here, I think it doesn't contain a closed curve. In the case of Marie Charpentier, where she proved that it's a continuum. If it's an undecomposable continuum, it will not contain a closed curve. No, it doesn't contain a topologically closed curve. Yeah.
All right, let's have more discussion over coffee and to thank Claude again.
Okay.